Hi everyone. In this video, I'm going to introduce the idea of a quantum mechanical state. And when we talk about a state in quantum mechanics, what do we mean by that? And additionally, I'm going to introduce the idea of a Hilbert space, which is a vector space where quantum states live. So it's a mathematical space where these objects are going to live. Before we can talk about quantum states, let's just talk about classical states. So what do I mean when I talk about a classical state? And this could be the state of a system of objects, or it could just be the state of a single particle. But this is going to include information about the system, such as the position. Here, maybe we're thinking about just an electron or something. Momentum, energy, angular momentum, right? All the things that we might measure. And generally, when you're doing classical mechanics, you think of these things as functions of time. So an object, we can think about its state at a given instant in time, and then we think about how these things evolve. So here, again, I'm not thinking about relativistic theories at all. I'm thinking about non-relativistic theories where position is a function of time and we watch how it evolves in time. And again, you can think about an individual particle, or maybe you have a box of particles, and then we know all the positions of all the individual particles and all their momenta. Then, representing this state mathematically is going to be hard if we have a lot of particles, right? But that's what I'm talking about when I'm talking about a classical state. Now, when I use the word state in quantum mechanics, things get a little bit more complicated. A quantum state is complicated by a couple things. So in general, a quantum state, we're going to want to talk about these same sorts of variables that we measure: position, momentum, energy, angular momentum, etc. But you will have learned already in your modern physics class about the superposition principle, right? This tells us that an object can be in multiple classical states at the same time in some sense, right? A system can be in multiple classical states at the same time. For instance, you will have learned about a wave function, which describes the position of, for instance, an electron. And the wave function tells us that there's all of these probabilities for the electron to be in all of these different places. So before we measure the position of the electron, and there's a sense in which it doesn't have a definite position. Instead, there's just this sort of probability cloud describing the location. So whereas classically, when we were talking about the classical state of some particle, it just has some position as a function of time. Now we need this more complicated object, again, in the example of position, which would be a wave function, and this wave function is evolving in time. So this becomes a more complicated thing. The other complication that comes out of quantum mechanics is quantization. So all of these properties classically live on a continuous spectrum. So instead of position, let's think about angular momentum now. You can have an object which is rotating and so has some associated angular momentum, and it can be whatever number you like. In quantum mechanics, we know that there's something called spin, which is sort of like angular momentum. Um, Although it's this different intrinsic form of angular momentum. And we learned that if we measure the magnitude of the spin for an object, it takes on discrete values. It can't take on any value that we want. It only, for a spin, right, it's either spin up or spin down. which is the values h bar plus or minus h bar over 2. You also, if you have seen, for instance, the harmonic oscillator, you learned that for a quantum harmonic oscillator, the energies that are allowed are quantized. That object, which, just a classical harmonic oscillator is just a mass on a spring. And classically, this mass on a spring can have any energy that you like. There's an infinite number of possibilities. A quantum harmonic oscillator can only take on values with these finite energy levels. So that's going to add additional complications, right? So again, by quantization, I mean for some observables, only discrete values can be measured. And this is as opposed to a continuous spectrum. All right, so we're going to need to think about how we can create some mathematical framework to describe these odd things that happen in quantum mechanics that sort of complicate our quantum mechanical states. And what we're going to find is that linear algebra will be a natural home or a natural language for quantum mechanics. So in modern ways of thinking about quantum mechanics, really, if you're doing quantum mechanics, it's applied linear algebra. And this is going to be a very, very natural home for quantum mechanical states. So these states, quantum mechanical states, are going to live in what is known as a Hilbert space. This is, in linear algebra language, this is known as an inner product space. Which is really a vector space with the ability to calculate something known as an inner product. Okay, there might be some other mathematical subtleties to the definition, but for our purposes, this is good enough. So in your linear algebra class, you learned about vector spaces, and a Hilbert space is basically just a vector space. And the vectors in this space are going to represent our quantum states. So I should state that, and I'll state it right here as our first axiom of quantum mechanics, which is that a quantum state is represented by a normalized vector in a Hilbert space. And this normalization requirement is going to be related with the interpretation of probabilities in quantum mechanics. So this is required by a probabilistic interpretation of quantum mechanics. Oops. And we're going to see all of these things. All of these things we're going to unpack a lot more. Here I'm just trying to sort of define some of the terms and give you a broad overview. So this is our first. I'm going to put this in a big red box, because this is really one of the fundamental things. And here, this is right away, we're seeing we're defining our axioms of quantum mechanics, or we're writing our axioms of quantum mechanics in the language of linear algebra, right? It's going to be some vector some vector in a vector space. Okay, so let's think about these Hilbert spaces, these vector spaces in an example. And let's first think about electron spin. This is one of the first examples that often you see in quantum mechanics classes because it's a very simple example, even though spin is sort of an unfamiliar thing. So what is the electron spin Hilbert space? Oh, and I should have stated this before because this is just a general fact. I really I'm going to erase this because I want to state this general fact and make sure no one thinks that it's just a part of that example. All right, so one very important fact about Hilbert spaces that I forgot to mention is Hilbert spaces have as many dimensions as outcomes are possible for a given measurement. Right? This is, we were just talking about the fact that in quantum mechanics, things are quantized, right? Right? Which is to say, if you have some particular thing that you want to observe, some particular thing that you want to measure, rather than having an infinite number of possibilities in general, you might have some finite, discrete number of possibilities. Maybe it's still infinite, like the harmonic oscillator, the number of different energy levels you can have is actually infinite, but they're discrete. And so our Hilbert spaces are going to have as many dimensions as outcomes are possible for a given measurement. And that means Hilbert spaces often will be infinite dimensional things. Like I said, for that example of a harmonic oscillator, there are these discrete energy levels, but there are infinitely many possibilities. If you have as much energy, if you have an infinite amount of energy to throw into that harmonic oscillator, you can do that. So how you can visualize an infinite dimensional vector space is hard because you need an infinite number of axes. So we won't always be able to visualize that, but okay, let's look at some examples to help clear some of this up. So let's look at that example that I was about to say. And this fact that I just stated will make it clear why the electron spin Hilbert space is a nice one. So recall this electron is spin 1/2, and the spin can be, if you measure the spin of the electron along a particular axis, the outcome is always up or down. So there are two possible outcomes, up or down. This means this is just a two-dimensional Hilbert space. So sort of therefore, the Hilbert space has two dimensions. Just like when you were thinking about vectors from your intro physics class, whenever you write down a vector or draw a vector, you first want to choose some coordinates that you're working with. Are you working with Cartesian coordinates? Are you working with polar coordinates? Which direction is your x direction? Or you want to rotate them, right? You have to choose. So in the same way, you always want to choose some coordinates, which we're going to think of as our basis. So you want to choose a basis in which to represent your vectors, which again, these vectors are going to correspond to our quantum mechanical states. And again, you should think about this choosing a basis as just like choosing coordinates. So for example, we can choose to focus on the z direction. Spin, oh, I should say spin in the z direction. And then our Hilbert space, which is two-dimensional. So we can draw it if we like. It's going to have two axes, and our two axes are going to be our two possible measurement outcomes. So one possible measurement outcome is up, and the other one is down. And then a quantum state is some vector. So this might be a general state. And there's some notation that we use to represent our quantum mechanical states. Which are, and this maybe I'll draw a line here because this is not in this example. This is true in general. A quantum state is represented by something called the ket vector. Where the psi here is sort of telling you, it's labeling what state you're talking about. And these two, this line and this arrow, are sort of brackets around it. And it's telling us that, if I just wrote psi here, so that might be some function, I don't know what it is. This line and this arrow are telling us that the thing inside it is a vector in a Hilbert space. So back to our example we were just working on. So my general state, I would normally write as psi. And then we can consider our basis states, which we'll talk more about in a second, up, which maybe I would write as plus z, and down, which I might write as minus z. And these are our two axes. And a general quantum mechanical state is a superposition of these two. So quantum mechanical states in general are superpositions over or of these basis states. Oops, what just happened there? Which we'll talk more about in general. Let's look at another example, which is the position of an electron. The Hilbert space of that. In general, if we just have some free electron or even an electron in some potential, in general, it can be anywhere, right? A free election, or again, it doesn't have to be free. So an electron can be an infinite number of places. Which means it's Hilbert space describing the position of an electron, or the possible states of the position of an electron, is infinite dimensional. I can't just draw it because I would need to draw something with an infinite number. I can't, I don't know how to draw. You can't draw this, right? It's something with an infinite number of different axes. And so the way we're going to think about, there are going to be certain observables in quantum mechanics like spin, which are kind of nice because they have these finite number of outcomes when you measure spin. And so we can have this nice Hilbert space. On the other hand, some other observables like position and momentum, that where there's an infinite number of possible outcomes for a given measurement, is going to have an infinite dimensional Hilbert space, which we'll be able to deal with, right? You've already dealt with it. This is going to lead up to the notion of a wave function. But, um, but in a way, wave functions, they're more familiar because position is a more familiar type variable, but they're also more complicated because of this infinite dimensional business. Okay, so again, all of this is going to be more unpacked. I'm just trying to give a basic overview. Another thing that we're going to need, so I said the Hilbert space is a vector space with something, the ability to compute something called an inner product. So in order to do that, we're going to need to define what is known as a dual vector space. So for every vector, so for our Hilbert space, we'll have a Hilbert space, and then we're going to have a dual Hilbert space, where for every vector in your Hilbert space, there's going to be some dual vector. So for every vector psi, there will be a dual vector, which we'll write this way in a dual Hilbert space, where this thing here is called a a bra vector, excuse me, a bra vector. And then, and we'll see, we haven't really talked about how to actually quantify these things or expand them in any way right now. I'm just sort of introducing some notation where, again, psi is really denoting the particular state, and then this line and this arrow pointing now in the other direction is telling us that this represents an object that's not just, again, a function or something. It's instead a vector, and it's a vector that's living in the dual space. So the arrow is going the other way. With this dual vector space, we will calculate an inner product. So the inner product between two states, psi and phi, is written as psi phi, where this now, read aloud, says bracket or bracket. Which is the origin of these silly names we have. And what this inner product ultimately is going to be associated with is how similar these two states are. This will be related to how similar these states are. So the inner product is going to be something like an enhanced dot product. So when you first learned about dot products, you learned if we have two vectors and we take their dot product, it's maximized for vectors that are parallel. And then if we have vectors which are perpendicular to each other, the dot product is 0. And if we have two vectors where they're sort of aligned, then, it's not a maximum value, but it's bigger, right? And so just as the dot product sort of tells you something about how aligned, it's bigger if your vectors are more aligned. The inner product here is also, it's going to tell us how similar our states are. Okay, so this didn't tell you anything about how to calculate this thing, but hopefully it introduced some of the key notation and some of the key terminology that we're going to unpack in videos going forward.